Remember our first domain was a triangle. I'm now going to make this a parallelogram. Okay. So the bounds are j equals max of 0 and I plus n or something like that. This line is j equals, sorry, I minus n. J equals I minus n. And this is I equals j, right? So the upper bound is j, a min of j and n, or n minus 1. Okay. So I just changed the upper bounds and the lower bounds so that each column is evaluated at points in this triangle. Okay. I'm going to do this to introduce something interesting that happens. Okay. My reuse is still along 1, 1, right? The expression hasn't changed. The only thing that has changed is the boundaries. My accumulation is always vertical or remains vertical. My reuse is diagonal. What happens when I shift the domain? I get this, right? And by the way, if I'm accumulating along columns, my answer is now from 0 to 2n. Okay, y is, the size of y is increased. Okay. What happens? You know, in the previous example, I had the right boundary that disappeared. Okay. This boundary does not disappear, right? So this boundary is also along the direction of rho, so it is going to be included in the intersection. So this boundary is invariant, this boundary is invariant, this boundary is exposed, right? And what is happening over here? If I look at one column to the next, take this column and take the next column. Okay, this column is the accumulation of all these values, and this is the accumulation of all these values. So here is a value that occurs on the left but does not appear on the right, in the column on the right. When I shift, this is a point that is to be removed. It does not contribute anymore to the answer, right? This answer is the sum of all of these. This answer is the sum of all of these. Okay, but the upper bound is at n. So the left column is higher or has more points than the right column. In other words, when I do this transformation, I have one boundary that is from the original domain, one line, and I have one line from the shifted domain. So if I compute d minus ds, this is the notation for set difference, and I compute ds minus d, those are the two sets of facets where I may have residual computation left. Okay. So this is a new domain, which is a subtraction domain. So y of I is going to be y of I minus 1 plus, one of the y terms from here and minus the y term from over here, right? Agreed? Another way of thinking about this is the following. If I go back to my first example, okay, I shift to the right. Why not shift to the left? What happens if I shift to the left? I have my original domain and I shift it to the left. Okay, so I'm going to compute yi from yi plus 1 and something else. right? If I have all the answers in this column, how do I compute this answer? It is this answer to the right minus x I plus 1. Okay, minus just one term. So this is also linear complexity. So when I explained simplifying reduction, I gave you the easiest answer, but actually you can discover many different answers that are all linear complexity. By the way, what happens is that if I do it this way, I have a boundary condition. So remember when I shifted to the right, this domain disappeared. Well, now I have, when I shift to the left, what happens? This last domain, last column was in the original computation. And so I have to compute this as a boundary. I have to compute an accumulation of n terms to compute y of n. And then I compute every y as yi plus 1 minus xi plus 1. It is still linear time, but it is double the work. So it's not an efficient algorithm, but it's possible to do it. Okay. And it comes simply because of a different choice of row to use. Okay. Now I am going to ask you a complicated question. So what happens here? I compute my y, and it turns out that I have to either add this value or subtract this value. Okay. Now I'm going to give you 5 minutes to answer this question. Instead of sigma, instead of addition, I am computing max. So if I compute the max of all of these elements, and I ask you, what is the max of all but one element? Can you tell me?
So if that one element is not the max,
Yeah.
then the max stays the same.
No. But you have to look at that element and suppose I give a set of elements 3, 5, 7, 6, 19. Okay. The max of that is 19. Okay. And I can compute that as I'm increasing the sets incrementally. But if I'm decreasing the sets, from the max of this, can I compute the max of this? I give you an array of values, and I tell you the max of these n values is something. What is the max of the first n minus 1 subset of that?
So we will see the max of the array which is n minus 1 elements, and then we will compare with the max which is given, like for the whole array for n elements.
But how do you compute the max of the n minus 1 elements? That is another linear time work.
Yes.
That is because the max operator does not admit an inverse.
So it has to be reversible to
It
apply this.
has to admit an inverse operator. The accumulation operator must admit an inverse. Only then can I do subtraction. Okay. So when you have operators that admit an inverse, things are easy. But the moment you have operators like max, and this happens in dynamic programming kinds of problems, if the reduction operator does not admit an inverse, there are some additional complications when you do this simplifying reductions. For example, on my triangle, I have a space of reuse vectors to use. The row was along 1, 0. Any multiple of 1, 0 was allowed. Okay. If it wasn't if it was sigma, then I could go in the positive direction or I could go in the negative direction. And either way, I could get a linear time program. If this is a max, then I can only go to the right. Going to the left means that I have to subtract something, but there is no subtraction operator available. So the moment I throw in these max-like operators that do not admit an inverse, things become complicated. And the entire feasible space of reuse vectors that can be exploited can no longer be, the entire space cannot be. There are some reuse vectors that are not legal anymore. Right? So I go back to this question. If this is a max, can I do something over here? Can I still simplify this? My reuse is 1, 1. If I go along this way, along 1, 1, then this is an addition face and this becomes a subtraction face or subtraction boundary or edge or facet, okay, of the polyhedron. If I go in the opposite direction, then this becomes addition and this becomes subtraction, right? Because that came from the original one and this came from the shifted one. So we are in trouble either way. Can you think of somehow doing better than that? Can you still do this in linear time? What if I take this parallelogram? I have an answer, right? I have an answer that works on triangles. It doesn't work on parallelograms. So why don't I cut this parallelogram like this? And on this triangle, I shift it to the right. And so on this section of the inputs, I compute a prefix. So I shift it to the right. On this triangle, I shift that triangle to the left and compute this from this answer, right? So I have my input x. I take a forward max on it, and that is this answer. And this section of the final answer is actually the backward max on the same input. So I break my parallelogram into two triangles. On one triangle, I shift it so that this oblique boundary is addition, or this bottom boundary is addition. On the other triangle, I shift it in the other direction so that this also becomes addition, or this also becomes the max operator. There is no subtraction.
But sir, row vector is 1, 1 here, right? So we have to move via this diagonal, right?
I have to move in some multiple of 1, 1. I can move in the plus 1, 1 or minus 1, minus 1. And I'm saying take this triangle, move it in 1, 1. Sorry. Oh, you're absolutely right. My mistake. Move it this way and move other one this way. Yeah, that was the point, right?
Yes, sir. Yes.
Okay, good. Okay, so my apologies. This is the row vector. So this triangle is moved to the northeast and this triangle is moved to the southwest. And because it's moved to the southwest, this is a new face that is exposed. There is nothing that comes from the shifted domain that remains. Okay, when I take this triangle and shift it southwest, this new face is an addition face. It came from the original domain. Okay. How many of you have heard of max pooling? Yes, Vishnu? You're saying yes, you heard of it, right?
Yes, sir.
Okay. Okay, we might get there. Now I'm going to give you an extension to this. What if sorry. Same thing, except that y is unbounded. And therefore also x is also unbounded. Okay. Now what? So my domain is like this, right? It's an infinite strip like this. And here is my possible reuse direction, or that or the reverse of that. This thing should give you some ideas.
So you got many triangles.
You can get many triangles. So how do you get many triangles?
First we get many parallelograms.
First, we get many parallelograms like this. So, and then we cut each parallelogram into a triangle, right?
Yes.
And then each of these triangles that have a horizon, whose base is below, is shifted like this. Each of those is shifted down. But what is this answer over here? This answer is accumulation of the whole column, right?
Yes.
So some more stuff is still missing, right? You have to do some little bit more work.
So make it half because it will be make
Pardon?
it half. Like whatever we get, we make it half because we are counting.
Your voice is not very clear. Will you half, or I didn't get you?
Yeah, we will make like half it. Whatever we get, half
No,
it
it's not
because
half. You are going to compute two expressions. This may be 1/3 and 2/3, etc. Right? Right. So you are going to compute two sub-expressions, and the final answer is the max of those two separate reductions. You're going to split a reduction by this line into two reductions and combine those two answers with a max. So you're splitting the reduction. That's the new twist over here. This reduction in this triangle can be computed as a backward scan on this section of the input. Then you move on to this section of the input and compute a forward scan or forward prefix max, and combine it with that previously computed answer by a max operation. You do a backward scan of this same block of inputs, and that is the partial answer to the next block of outputs. Then you read the next, then you do read the next input and do a forward scan. Next block of input, do a forward scan and use that and update that block of answers. So you are doing 3 comparisons per pixel or per answer. Okay. And of course, this was one-dimensional, but you can extend it to images. And if you notice, what this is doing is a convolution. You know why this is a convolution? You're taking a window and you're multiplying all the elements with the coefficient 1. Okay? You're multiplying in the max plus semiring. Okay? The multiplication operator is the addition. The identity of the addition is 0. So you are convolving the input with some coefficients which is equal to the multiplicative identity. So what you are doing is a convolution in 1D. If you do it on images, you're doing a convolution. So a CNN with the max plus semiring with unit weights does max pooling. And you can compute max pooling with with constant time comparisons per pixel. And what I just described to you, see, I was, we were very happy when we thought we discovered this. Van Herk in 91 or 92 or 93 or something like that, around, so 20 years ago, this was already known. Too bad. And when we discovered it, it was 15 years ago, it was known, unfortunately. You know what though? I explained how applying simplifying reductions by hand can get you to some of these clever algorithms, but right now a compiler can't do this. You know why? How do you know what their pieces are? And there may be infinitely unbounded number of pieces. So, when should a compiler stop? What can a compiler do? So this is still an open problem of how to do simplifying reductions to discuss for a compiler to generate this 20-year-old algorithm. 30-year-old, sorry, 91. It's 2021. Our compilers today still can't do it. Okay, I think it's 9:30, so 9 o'clock for you. You guys have been quiet. Thank you for those of you who were asking questions. That actually does keep me, gives me the feedback to keep me engaged. I'm happy to take any questions about anything else that we talked about.
We'll stop the recording. Maybe you can ask some panel questions to sir as well, because it will be
So, Rama, I had this thing. Your panel is at 4 o'clock, right?
Right, very.
4 o'clock your time is like 4:30 my time. So I would appreciate that if you just record the panel and
Yes, sir. We'll do that. We'll do that. We are also circulating a Google form when they can populate the questions.
So again, that is actually a very important thing, that if you students have, you guys are participating in the panel on Friday. If you have questions for me, I will not be at the panel, so if you know, or the questions, feedback, or anything about, you know, about anything in the summer school, I am happy to answer your questions offline or now if you have any of them. If you have
So
any,
can you
so
suggest some resources, some where we can study more about it?
about which
Uh,
about simplifying
this
reduction.
reductions, yeah, simplifying
Simplifying
reductions.
reductions, there are 3 papers. There is. So this was the kind of expression that we had, right? No, this was what I had was a double accumulation. This was the one.
Yes.
Okay. So let's just look at the different reads. Okay. I have a 3-dimensional index space, right? Because I'm computing a 1-dimensional answer y indexed by I, and I'm doing sigma j, sigma k. Agreed? So there are these 2-dimensional slices along jk. I think there is a picture, but let me first talk about. No, there is no picture for this one. Okay, there's a 2-dimensional slice along jk, which is all accumulated. And the expression is ai j plus k and bjk. There are 2 terms that are multiplied inside. Agreed?
Yes.
If you look at the combined expression, it depends on I and j and k, and then there is actually really no reuse possible in the expression. But there are 2 sub-expressions, a sub I j plus k and b kj. These are 2 sub-expressions, and they're combined with an operator multiplication that distributes over addition. Okay? And the sub-expressions themselves have some reuse. Along the vector j plus k equals constant, so 0, 1, minus 1. The first term is shared. And along I, because b sub kj doesn't even involve I. So along the I direction, the same value of b is read, right? So the sub-expressions have reuse. The combined expression has no sharing. Okay? But along these directions, you know, I cannot somehow pull out something outside the sigma, right? None of these terms can be pulled outside the summation. Do you agree? You know, just think of it doing a sum
Yes.
of the
Yes.
algebra, right?
Yeah. Yeah. We can't pull it
Okay,
out.
you can't pull it out. Okay, so you cannot exploit distributivity. But instead of doing this sigma j, sigma k, if I do the double accumulation in a different way, what if I do first the sigma j? I could, I could do many other ways, but if I just swap the summations, I could do, right? Then the second term in the summation is independent of j. The bkj is, oh, sorry, it's not independent of j,
So
sorry.
independent of I.
Independent of, it's independent of I. So I cannot just swap the sigmas, right? But I am adding up points in a jk plane. What if I
Yeah.
add up first all the points along the 1 minus 1, along the anti-diagonal in that plane? Okay? And then add up those answers. So sigma jk doesn't have to be adding up just along the axes of the jk plane. I can add up some oblique sets of values. Okay. And if I add up those oblique sets of values, among those oblique sets of values, the same A is being used and it can be pulled outside that inner sigma.
Yes.
Is that what you did?
Yes. Similar. Anti-diagonal. We summed all the anti-diagonal of BJ.
Beautiful. Beautiful. So
So
a compiler, we have compiler technology that can
which can do that.
do what you
Okay.
just did.
So it took me like whole lot of analysis. Like then I was able to come up with it. So
Very
I
nice.
was
Beautiful.
so,
Beautiful.
but so this can also be done with the same technique where
This
we
is
can
fully
see.
automatic. Yes, this is fully automatic.
Yeah.
If we are a little bit beyond time, I'm going to tell you how this can be done. Okay. This thing, what I call reduction decomposition, appears in a different example. Okay. So, and it also explains why the problem is actually pretty complicated. Okay. So, if you are adding up like this and the green arrow is the reuse space, okay?
Okay.
And let's
Along
say that
the
my operator is max, so I do not have a subtraction operator. If I shift it like this, if I move the purple to the blue, there is one new face, but one face has to be subtracted. It was there in the purple, but not in the blue, right? And so overall, I have that face of the pyramid that has to be subtracted and the blue face that has to be added. Okay. If I try to exploit reuse in the opposite direction, then the other, it's not safe. It is exactly like what happened with this max plus, the max filter that I was showing you previously. Okay. But you know what? This time I don't have to invent any clever tricks. Why am I adding up a whole double summation or double max of a whole slice? Why don't I break up my accumulation as first a set of accumulations along columns, and then I produce an answer on the yellow triangle, which I accumulate with the max operator to produce y. So I'm decomposing the double reduction into two reductions, both of them one-dimensional. Okay? If I do that, then I only have to look at one column to the next, and the purple column is completely contained in the blue column. There is no subtraction phase that is involved. Okay? So now I can simplify this in quadratic time. And now in this final answer, I compute this. So there is only one dimension of reuse and it can be exploited. Okay?
So
yeah, go ahead.
So the multiplication, the operator that was in between, so it was commutative. So that's why we were able
Because the
to.
distributive property, one of the
It has.
terms is pulled out of the sigma because it was combined with the other term using multiplication. You're doing reduction with one operator addition, and inside the expression there is a multiplication which distributes over addition, and the distributivity is the property.
Distributivity is there. So if
right?
the distributivity wasn't there, then there won't be a
And there is
solution
no.
for this.
Yeah, absolutely. Okay, so it's a combination of many different things. There is a distributivity, and there is a need for doing this oblique decomposition of the reduction.
Okay.
Thank you all for the opportunity. It was really a pleasure.